All right, so now what we're going to be doing is we're going to talk about triple integrals, but we're going to be changing our coordinate system. So we're going to be looking at triple integrals in cylindrical, starting with that, and then a little bit later we're going to be looking at triple integrals in spherical, except for the fact that that's going to be on a different video, right? Because I want to go, I kind of want to separate that out the two and think about the two differently. So what I'm going to do is I'm going to look at, I've got an x, y, and z axis right now, okay? So I've got the xy plane, okay? And when we start talking about in 3 dimensions, we want to shift, we want to stop calling it the xy plane, and we're going to start calling it the r theta plane. All right? So it's going to go from the xy plane, and we're going to start calling it the r theta plane. And you're going to see that a lot when we talk about spherical, we start talking about polar. It still is the xy plane. What happened is that we changed the coordinate system. So the coordinate system now is in terms of radii, and it is in terms of radians around the z-axis, right? So we're going to imagine that we're moving around the z-axis, okay? And so we'll start out here, okay? This thing here, the x-axis actually has another name. It's going to be called the polar axis, okay? And we're going to start out with, this is theta equals 0, okay? And so, right, we've got, if we remember that we're going to go around on that xy plane, or now the r theta plane, we're going to go, and that's going to be 0 to 2 pi is 1 revolution around, and that's going to continue to be the same. And then, in addition to that, we talk about radii, r, okay, and r is a distance from the origin out to a particular point, okay, so that's r, and so r is basically a length, and now our coordinate system is going to be in terms of r and theta, and then we're going to add in a z, all right? And the cylindrical system basically just changes the xy plane into the r theta plane, and then has the z-axis. And the reason why it's called cylindrical, we'll see in just a moment, is because we can actually define cylinders in a very, very simple way using the cylindrical system, right? And hence why it's called cylindrical. It's like when we talk about spherical, you'll see that a sphere is actually defined in a very, very simple way, okay? Now, what you'll notice is that r is the distance from the origin to a point on the r theta plane, okay? So it's not like out here, like this distance here, if I went out, and I'm not on the plane, I just come out to this point right there. That point right there, that's not r, right? That's not r right there, okay? That distance. R is going to be just the distance on the plane, all right? So what we think about is we're like, okay, I'm going to go out R, say for example, if I have, we'll say 2, comma, pi over 2, comma 3, the way that's going to look like in cylindrical, okay, if you remember is that that's going to be 2 out, okay, in terms of distance, and I'll just do that distance on the x-plane, so that's 2 away on distance in terms of R. Then I'm going to move pi over 2. Okay, so there's pi over 2, that distance pi over 2. And then what I'm going to do is I'm going to straight up 3. Okay, 1, 2, imagine that that's 3. Okay, and so now that point right there is 2 pi over 2, 3. Okay, we'll do this one more time. We'll have another point, call this P. We'll have Q. And let's imagine that Q is negative 3, comma, pi over 4, comma, and then let's do negative 1. All right, so this is going to be R, this is theta, this is Z. So R is going to go negative 3, so that means that we're going to go in the negative direction. All right, so just imagine that we're going kind of backwards. So there's R equals negative 3. I'm now going to go pi over 4, okay? I'm going to go pi over 4. So what that's going to look like is I'm going to go pi over 4. So I'm going to go halfway through here. So it's kind of sitting there behind the z-axis. And then I'm going to go down negative 1, right? And so you kind of imagine, it's below the r theta axis, right? It's kind of right in there. And you just have to kind of imagine, because you're looking three-dimensionally, that you've got that point right there. And that point ends up being negative 3, pi over 4, and negative 1. Okay. Generally, when I'm drawing points in cylindrical or polar, or spherical. I kind of go in that order. I go in the order of figure out what r is first, then I'm going to do theta, and then I'll do z. You could theoretically go in any order that you want. It's just kind of difficult to think about movement away from, in terms of your theta, away from theta equals 0 if you're somewhere else, right? So sometimes it can get a little complicated. And so that's kind of where I start out with as I'm working in cylindrical. So now that we have a notion of the graphing system inside of cylindrical, let's look at like the conversions for rectangular into cylindrical, okay? So basically what we've got here, right, if you remember, so in rectangular, what we got x, y, and z. And then in cylindrical now, we're actually going to have r, theta, and z, okay? Now z is z, all right? So if we actually think about our conversions, okay, conversions here now, z is just going to equal z. X is going to equal r cosine theta. And y is going to equal r sine theta, just like we had before, okay? So basically, it's polar, right? So we've got polar coordinates here, and then we've got z, all right? And so cylindrical can kind of be simple to think about because of that, for that reason. Now, if we want to go backwards, right, okay, and let's imagine, so this is going from rectangular to polar. If we want to go polar back to rectangular, just as a reminder, okay, then we know that we're going to get r is equal to the square root of x squared plus y squared, okay. We also know that theta is going to equal, actually this goes from polar to rectangular, and this goes from rectangular to polar. And theta is going to then equal the tan inverse of y over x, right? Basically, the tan inverse of the slope of whatever triangle you're developing. And so, as we look here, we've got on the r theta plane, right, which is the xy plane, we're going to imagine that we have a triangle, okay? And so, this is, if we just think horizontal distance, this is x, it's going to equal r cosine theta. This distance here is r, which is going to equal the square root of x squared plus y squared. Okay, this is y, it equals r sine theta. Okay, and by the way, so this is only two-dimensionally. Okay, and then if you think about it, tan inverse, if this is theta right there, that's theta, then tan inverse of tangent of theta is going to just equal y over x, right? Because that's the sine of theta over the cosine of theta. And so that's how we get the tan inverse of y over x. And then z, just a z coordinate. So there you go. So now that we've got kind of like our coordinate system, and you want to make sure that you do know this. This is the kind of thing that really you want to have memorized. We're going to use it a lot. Okay, so it's kind of thing you're like, okay, I want to make sure that I know this. Let's actually see why it is that we utilize something like this and for something called cylindrical. Okay? So what you should be thinking whenever we change coordinate axes is we should be thinking, you know what, the reason why I'm changing my coordinate system is because it's easier to do computation, it's more efficient, or it's easier to imagine working in a different coordinate system. And that's actually why we make conversions into cylindrical. So let's give a couple of examples, okay? Let's first think about what a cylinder is, okay? So a cylinder, so we're gonna imagine that we've got this cylinder here, and we know that if I take r equals and some constant, we're going to call it r equals k, okay? And for our purposes, we'll use r equals 2. All right, so that is in polar, right? In polar, that's a circle of radius 2. So in polar, we're going to have a circle of radius 2. In cylindrical, that's going to end up being a cylinder of radius 2 with like any value of z that we want. So it's what you imagine is you kind of like imagine that you've got this infinite cylinder, okay? Because on the r theta plane, okay, what we've got here, like I said, we've got a circle of radius 2, okay? So here's our circle of radius 2 on that r theta plane, okay? And then z can be anything. Z is what we would call free. right? It can be anything that we want it to be, okay? And so consequently, what we want to imagine is that you just end up having the circle on every plane for every value of z. And so hence, r equals some constant in cylindrical is literally a cylinder, right? Okay, so this form is a cylinder in cylindrical. And if you can imagine, if say for example you're integrating, okay, how much easier is it to think about like integrating over just a constant value versus, say for example, if we were to rewrite this in rectangular it's x squared plus y squared equals 2. And then we probably have to change it out to being y equals the square root of x squared minus 2, right? And we're going to have to use the plus or minus. We're going to have to use bottom and top. So it's like, oh, okay, if I've got a cylinder that I'm actually integrating over as my volume, that's totally what I'd rather use versus this. This is a pain. It's a mess. It's really hard, right? Very inefficient. 2 variables versus 1. Not something we want to do, okay? So consequently, what we want to be thinking about is we want to think, okay, that figure there, okay, that cylinder is represented with a very simple equation, okay? So there's another one. Let's take a look at another figure actually that ends up becoming very simple instead of cylindrical as well. So another figure that ends up becoming very, very handy for us to be able to draw in cylindrical is a plane that passes through the z-axis. So once again, let's take a look at what this looks like, okay? So we want to imagine that what I've got here is I've got so I've got some kind of like, you know, I want to imagine I've got this plane here that's going to pass through the z-axis, all right? And there we go, and we can even imagine that it kind of goes downward forever, right? It comes outward forever. This is just like a cut of it that kind of gives me a sense of what it looks like, okay? So what we've got here is we've got actually a plane. Now, if you think about this, what this is, okay, is that this is just every value for r and theta, r and z, any value that we want for r and z, okay, and it's just a particular theta. So like say for example, this one we would have it be theta equals pi over 3, okay? So theta equals pi over 3, any value for r is going to allow us to move backwards and forwards on the r theta plane, okay? And then any value for z is going to allow us to go up and down. So any plane that passes through the z-axis can be written as theta equals some alpha. So theta equals some alpha is a plane that lies on, basically a vector on the r theta plane of theta equals alpha. So that plane is also super easy to like actually, you know, draw and write. So if we can actually have something that we can rewrite utilizing that plane, it's way easier to work with versus, you know, what it would be otherwise. If we were to rewrite this from going from our cylindrical back to rectangular, what you can see is right that we've got theta equals tan inverse of y over x, okay? And in this case, pi over 3 is equal to tan theta, so, or is equal to theta, so tan inverse of y over x equals pi over 3. We get tan of pi over 3 equals y over x. Remember, tan of pi over 3 is going to equal the square root of 3. So square root of 3 equals y over x. And so consequently, y equals root 3x is this plane. And again, what we have here is we actually have an equation in 2 variables, or well, equation of one variable, not a constant, right? Not a constant function. This thing is harder to use than this one right here, okay? That's just an easier function to use. It's an easier function to integrate around, and a reason why we're going to use cylindrical. So if we're going to transform this into a theorem, and we're actually going to make a statement about like what is it exactly that we're doing when we change something into cylindrical, let's go in and we'll, Fubini's theorem for cylindrical coordinates. We have a function g, x, y, z is continuous on some rectangular box B, which we can then describe in cylindrical coordinates, looks like, and then we get b, just like we stated here before, it's r theta z, R greater than or equal to A, less than or equal to B, theta greater than or equal to alpha, less than or equal to beta, and Z greater than or equal to C, less than or equal to D. And then we can rewrite G of XYZ to equal G of R cosine theta, R sine theta, Z, and that'll equal F of R theta Z. So that's our changeover for our function from rectangular into cylindrical. And the triple integral over B of gxyz dv ends up being the integral from C to D, the integral from alpha to beta, the integral from A to B of F of R theta Z, R dr d theta Z, dz. Okay? And so that's exactly like what we just actually kind of talked about a little bit, but this is actually the statement and the actual statement of the theorem that we're looking at. Okay? So let's take a look at an example. So let's take a look at, let's integrate over the region B of zr sine theta, r dr d theta dz, where B equals the integral, or the region, r theta z such that r is greater than or equal to 0, less than or equal to 2, theta is greater than or equal to 0, less than or equal to pi over 2, and z is greater than or equal to 0, less than or equal to 4. So we're just going to go over, this one is just going to be our general, our general setup. Let's imagine what this region actually does look like, okay? So we'll draw out the region. It is going to have, we're going to have R is going to go from 0 to 2. So 0 to 2, those are going to be kind of our bounds for R. Then we're going to have theta is going to go from 0 to pi over 2. So again, we're going to go out from 0 to 2, and we're going to imagine it's going to be that just that first octant, okay? And then z is going to go from 0 to 4. So our z is going to come up to here. We imagine, okay, there's that portion right there. Okay. And then there's this portion. So it's kind of like a quarter cylinder. It's that quarter cylinder right in there. Okay. So that's the volume that we're going to be integrating over. So our integral will be set up. The integral, notice that we have dr first. So that means that our r values, we're going to go from 0 to 2 in r, 0 to pi over 2 in theta, and then we're going to go from 0 to 4 in z. This function is actually all written already as a function of r, theta, and z. So we got z, r sine theta, r dr dz, or r dr d theta dz. Okay, and that actually I think for our book is going to be more common. Excuse me. So notice this is going to actually give us r squared. If we rewrite, we'll get the integral from 0 to 4, integral from 0 to pi over 2, 0 to 2. It'll be, let's do r squared, z sine theta, r d theta dz. We'll now integrate with respect to r only, keeping the theta values and the z values constant now. So that's going to give me 0 to 4, 0 to pi over 2, okay? R cubed over 3, we'll evaluate that from 0 to 2. And this is then going to be z sine theta, d theta dz. If we kind of pull this out a little bit, just do a little calculation here. This is going to be then 8 over 3 minus 0 over 3, which just equals 8 over 3. And so that's now constant, so we can pull that constant out. We'll make this 8 over 3 times the integral from 0 to 4, 0 to pi of z sine theta, d theta dz. So now we're just going to integrate with respect to theta. So we've got the sine of theta. The integral of the sine of theta is going to end up equaling cosine theta. So this is going to be 8/3 integral from 0 to 4. And this will be then cosine theta evaluated from 0 to pi over 2. And then z dz. So cosine theta, cosine of pi over 2 minus cosine, oh, this should actually be negative, shouldn't it? Negative cosine pi over 2 minus cosine of 0, negative cosine of 0, excuse me, is going to end up equaling positive 1. All right, so that's positive 1, and so that's 8/3. times the integral from 0 to 4 of z dz. And now we just got to integrate with respect to z. We got 8/3 z squared over 2, evaluated from 0 to 4. And so that's 8/3, right, times 16 over 2 minus 0. So that's just times 8. So that's 64 over 3. And that is the value for our triple integral. Okay? So once we've actually got it set up, then it's just a matter of doing our triple integral. There it is. There's the whole process. Is it a long process? Yeah, it is. I mean, you know, what are you going to do? That's integration for you, and that's triple integration in particular, but it pretty much follows the same process as what we were doing before. So let's do some setting up, and I think the setting up of these integrals is actually going to be the most important thing for us. Let's consider that we've got the region E inside the right circular cylinder with equation r equals 2 sine theta, and it's bounded below by the r theta plane and bounded above by the sphere with a radius 4 centered at the origin. Now, we're going to set up a triple integral over this region with a function f of r theta z in cylindrical coordinates. So what this is going to look like, we're going to first ask ourselves, we're going to need bounds, we're going to need some bounds, and that's really what we're going to be looking at here, the issue that we got. So our bounds, we're going to need bounds for z, okay, we're going to be bounds for r, and we're going to need bounds for theta, okay? So let's first take a look. It's going to be this cylinder right here, so that's the region that we're going to be looking at, okay? And it's going to be bounded below, if you think about z is going to be bounded below by 0. Okay, so we're going to go from 0 less than or equal to, and it says bounded above by the sphere with radius 4 centered at the origin. So the equation for a radius with for a sphere is going to be r squared plus z squared equals 16 for that bounded at the origin. And the reason why is that normally the equation for a sphere of that nature, x squared plus y squared plus z squared, is going to equal 16. Okay. This is actually r squared, so we replace that with r squared in cylindrical, and it becomes r squared plus z squared equals 16. Okay, so when you're looking at a sphere, this is actually the general equation for a sphere inside of cylindrical. So that's going to be our upper bound for z. So z is going to be bounded above by, we'll rewrite this, z squared equals 16 minus r squared, okay? And we're only interested in the top part because we're going to bound below by the r theta plane, right? Bound below by the r theta plane. So we're only going to be interested in z equals the square root of 16 minus r squared. We don't need the whole cylinder. So that's going to be the top part for z. So this will be the square root of 16 minus r squared. And those are going to be the bounds for z. Next up, I want to consider r. So r, okay, the boundary for r, okay, so the first r, right, if we notice here along this cylinder, that value for r is actually 0, okay, so r is going to be bounded below by 0, okay, bounded below by 0, and then it's going to go out to places on essentially this circle if we think about it on the r theta plane, and that circle is given by r equals 2 sine theta. So r is going to go from 0 to 2 sine theta. All right, and so that's going to be the bounds for r. And then finally, we're going to be looking at theta. And sometimes this gets a little tricky. Notice that this function is only in the first quadrant. So it's only inside of the first quadrant, okay? And it turns out, right, that we're going to just go from 0 to 0 to pi, okay? So it's actually just going to go in from 0 to pi. And the reason for this is you notice that you're going to start here at 0. So that's, if I plug in, right, 2 sine of 0, that equals 0. And you're going to end up back at 0. One full revolution. So 2 sine of pi is also equal to 0. So you're going to go from 0 to 0. And that's why we're going from 0 to pi. Okay, so theta is going to be bounded below by 0 and above by pi. So now that gives me the bounds of integration for my figure here. So what we're going to get now is we got the integral. We're going to do z first, right? Because we're going to do r. We're going to r d theta dz, okay? So z is going to be on the outside. Well, no, we don't want to do that. We want to put theta on the outside because theta is actually given by some constant values. So we're going to go 0 to pi. And then notice that r is just being given by theta. So let's just do this. We're going to have r be next, and we're going to go 0 to 2 sine theta. And then finally, z is going to be as a function of r. So what we'll do now is we'll make this from 0 to the square root of 16 minus r squared. And so then it'll be f of r theta z r dr d theta dz. Okay, and that actually ends up being the function that we'll use to do our integration. Okay, so what we did here is we said, okay, let's consider the information that we're given. We're going to bound below by the r theta plane. Anytime you're bounding below by the r theta plane, then z is going to be bounded by 0. Then we have a function, and it's actually this sphere here, and so it's kind of a sphere that goes actually all the way around, if you kind of imagine it. And that's going to be the top end for our function. All right, so that finishes up for us finding volumes, doing triple integrals in cylindrical. We've seen a lot of different examples of how to go about actually setting up these volumes. They take some practice, because you're going to see a lot of different ways to, transform something from rectangular to cylindrical. Sometimes like really setting up the volumes and kind of considering your regions can be a little bit challenging at times. So I do recommend that you spend a little bit of time doing this, getting some practice in, maybe even doing some graphing for it too. All right, so there you go.